First talk. Okay, I need to leave another 30 seconds. Hey, it's inevitable, right? It's going to happen. One of the reasons we're trying. All right, so the title of the first paper is on the screen: Practical Monotone Temporal Planning. You can look at it. I'm very confused. Anyway, the talk will be presented by Dorian Frank.
So hello everyone. So as I said, I will present you the paper Tractable Monotone Temporal Planning. So it was written by Mr. Cooper, Maurice and Renier, and I'm for in front. I present it to you. So first, I'll begin with some reminders about planning. Then we'll see in detail what is this new tractable class for temporal planning. Then we'll see an important aspect of this class, that is monotonicity detection. Then some constraints in order to solve this problem before we conclude. So first, in planning for the complexity, in the general case it's intractable. For the propositional planning, the complexity is space complete. And in temporal planning, that is the domain that interests us, just testing the existence of temporal plane is p-space R if we don't allow the instance of the same action to overlap. And in the contrary, if we allow this instance to overlap, it's space complete. So for now, the tractable classes are based on two different things. There is a syntactic restriction on the set of operator, and also the restriction on the causal graph structure. So for this paper, we used the PDL 2.1. So the specificity of PDL 2.1 are that the action at duration, the condition can be at start, at the end, or over all the duration of the action. And the effect can be at start or at the end. So quickly, temporal planning problem is a triple IAG, where I is a set of fluents represented in the problem's initial state. A is a set of actions that are usable in order to attain J's goals. So there is a sub-problem in temporal planning that is solvable that can be solved in polynomial time. So this new tractable class can be solved in cubic time and in quadratic space. And also a temporal plan can be found with the same complexity with a minimum number of actions. So now I'll give you some definition in order that are necessary in order to understand what this class is about. So first, the set of sub-goals. Quickly, that is the goals that might help to achieve the goal, to obtain the goal. In the same way, the reduced set of actions are the actions that might be useful in order to attain the goal. So the calculation for these two different sets are big O and square. Another definition is the establisher unique. So a set of actions is establisher unique relative to the set of fluents if for every of these fluents there is at most one action that established it. So again, it's polynomial time to detect whether all the actions of a set are established unique relative to a set of them. So here's an example. If we have here's the arrow, the A, B, C, D, E, F, the action, and the arrow that are full established affluent, and those who are dashed destroyed. Here we can see that the action A is established unique of the fluent W. Even if there is two actions or more that destroy. Also an action can be established unique of many fluents, like for D, that is established unique of X and Y. But for E and F, these are not established unique of the fluent Z. The last definition is the definition of monotonicity. So there is a minus monotonicity. So it is set of a fluent that is the minus monotone if in any temporal plane, once it's been destroyed, it can be re-established again. So here's some example. For a person, if a person is the fluent of a person is alive, once it's there, of course, it can be put back to the state, to the previous state. So it's minus monotone. The same can be said for a match. Once it's lighted, it can come back to the state never used. In the same way, there is a definition of plus monotonicity. So for any temporal plane, if a fluent is established, it can't be destroyed. So again, some example, for a person to be graduated, can't lose this diploma. For a balloon to be exploded, can go back to the previous state, and for a nail to be hit. So the monotonicity of fluents, in order to determine if a fluent is monotone or not in a temporal plane problem, the complexity is very hard for this, because it's piecewise hard if we don't allow the same instance of an action to overlap, and if we allow this instance to overlap, it expects complete. So here we have the set of temporal planning problem. Here we have the problems that which we have two hypotheses, that is, the set of reduced action is established unique relative to the subgoals, and the monotonicity and the subgoals are all monotone. So these problems can be solved in polynomial time. But it's not enough to define this as a tractable class, because the tractable class can be solved, this problem can be solved in polynomial time, but also detected in polynomial time. And just as I said earlier, monotonicity can be very hard to detect. So that's why in the paper we define some rules that allow us to detect in polynomial time some of the monotonicity. So here in yellow we have actually the tractable class that are the two hypotheses, but the monotony can be detected in polynomial with output. So here's the formal definition. For a temporal planning problem, if we have the set of reduced actions that is established a unique relative to the subgoals, then if all these subgoals are monotone, and more specifically, if all the subgoals that belong to the initial state are minus monotone, and all the monotonicity can be found by using the following rules, then we have a problem that belongs to the tractable class. So for the detection, here is the first rule that we found. That is a more obvious one. That is to say, if a fluent, no action of the set of reduced action actually destroy a fluent, and there is and it's only added by some action, then of course, it's plus monotone. In the same way, if there is no action that can destroy a fluent, the fluent is monotone because even if it's established, it can be destroyed. For the second rule, there's 3 rules in whole, and the second and the third rule use the monotony of the fluent in order to find more fluent that can be monotony. So here's an example for the second rule. If we have AF, the unique action that establishes the fluent F, and P, minus monotone fluent. If we have the duration of the action A that is inferior to the duration of the action AF, then we see here that we have P that is a condition for AF, and F which is established by AF. So if the action A is used, we destroy the fluent F and we destroy the fluent P. But P is minus monotone, so it can never be established again. Then, since P is condition of the action AF, we can't use the action AF again, which is the only one who can establish the fluent F. So, with this, we can prove that F is minus monotone. So, in fact, this rule is a little bit more complicated. Here I present you the first condition. There is 4 different conditions. For each of the action that can destroy the fluent F, then each of these actions must at least validate one of these 4 conditions in order to prove that the fluent F is minus monotone. So we can see in the same way here. If we have once again the action AF that establishes the fluent F and the fluent P that is minus monotone, if the action AF destroys P, then we can't reuse the action A that have P in a condition. But here, with the definition of establisher unique, we don't know if there is other action that can destroy the fluent F. So for the definition of plus monotone, there can be another action that I don't have P as a condition, and which destroy F. So it's not enough to prove that F is plus monotone. So that's why we have, for all the action that destroys the fluent F, once again each of these actions must validate one of 4 conditions. So, once we have this problem that belongs to the class, in order to solve it, in order to find a plan, a set of constraints must be solved. So here is the form of the different constraints. With xi and xj that represent a particular instant of an action. For example, the instant where an action establishes a fluent or destroyed it. If we have this constraint on this form, then we have a problem that is STPD and can be solved in cubic time and in productive space by using the algorithm of Gerardini and Cristani for 1997. So here's an example that we used in order to test our rules. Here we have an example of a chemical industry problem. So we have some source, we have some catalyzer, and the goal is for 2 products, P1 and P2, to react. So here's the example of the solution. So we can see that here there is instance of the same actions that are done in parallel, like synthesize and catalyze. So all the constraints are found with the action. There is a causality constraint. We can see here, for example, that the instant where the action catalyzed establish the fluent catalyzing must be before the instant the action synthesized needs the fluent catalyzing. So that is the full arrow that you can see. There is also an authorization constraint. The instant where the action synthesized doesn't need anymore the fluent catalyzing, must be before the instant where the action catalyzed destroys the fluent catalyzing. Another kind of constraint that is not found in the example is the contradictory effects constraint. So obviously when one action establishes a fluent and another action destroys it, this instant can happen in the same time. So here is the translation of the STPDIF problem in an STN. So with this, we can see the beginning and the end of each of the action, and see all the constraints that are made. For example, the action here must be before other action and so on. So with this, by using the algorithm of Girardini-Cristani, we can solve it in order to find a plan. So to conclude, this is the first structural class for temporal planning. And also some common problem fit in this class. So I told you about chemistry industry, but it can be used in pharmaceutical industry in a lot of problems that is about manufacturing and creating things. So for the future work, you remember this graph? The objective is here to find new routes in order to extend the number of problems that we can detect and so the size of this structural class. But we can also imagine, by relaxing the term of monotonicity, extend the number of problems that are solved by using this one. So that's it. If you have any questions, feel free to ask.
Certainly time for questions.
Yeah, so I think the establisher unique, is that the same as the post-unique condition that Jonsson and Bäckström used?
Yeah, it's kind of the same.
So does that imply that there is some similarity in the actual algorithms to solve the problem, or it's just that this condition happens to be useful for different?
That is an hypothesis that in order to solve, it's restrains the different choices we have in order to solve the problem. But the main part here of the paper is about the monotonicity of the fluent. That is the new things.
Any questions? Our second talk is going to be entitled MD Propagation of Distracting Schedule, and the design will be Andres here.
Sorry, just some technical problems. for waiting. So I'm going to talk about new propagation techniques for disjunctive scattering problems. And these new techniques are based on multi-value decision diagrams, or MVDs. So first I'm going to give a brief review of what is a disjunctive scattering problem. Well, the idea is that you want to sequence and schedule a set of activities on a resource. So the activities, they have a processing time, and they must start after the release time, and they must end before a deadline. The resources, we assume that they are non-preemptive, so once you start executing an activity, you have to process it until it ends before starting the next one. And the main property is that in a resource, you can only process one activity at a time. Okay? And we have several extensions of this model. We may impose precedence relations between activities. You may have sequence-dependent set times. So between the end of an activity and the beginning of the next one, some time must elapse, which may be dependent on spare activities. And you may consider a variety of project functions. You may want to minimize make span, the sum of setup times. If your deadline is not a hard constraint, you may want to minimize the hardness, number of day jobs, and so on. Okay? And as you imagine, there's a huge amount of work already in this area. But somehow these works are spread into these two communities. On one hand, you have the AI planning community, which develops techniques that tries to be as much domain dependent as possible. And on the other hand, you have the operations research, which is the key phrase of the techniques in operations research is to exploit problem structure. And what is the consequence of that? The consequence is that all our techniques usually they work well in practice, but they are very hard to be extended, to be applied in other problem domains. And in AI planning, you have this rich, nice, and elegant modeling language, but when it comes to solving real industrial applications, then it becomes a little bit tricky. So what our work here is going to be the interface between these two areas, which is constraint-based scattering. Okay? So what's constraint-based scattering? In this case, we're going to provide a declarative description of the problem. So in the case of disjunctive scattering, usually a problem will look like this. You're going to define for each activity a start time variable, and the domains are going to be defined by release and deadlines. And then to enforce the disjunctive condition, you're going to impose what we call a global constraint, disjunctive. You're going to input the start times, processing times, and other parameters of the problem, and it's going to ensure that the activities they don't overlap in time. The idea is that each one of these global constraints, they have a specialized inference technique. Inference usually means reducing the domains of the variables, but it's much more than that. It's actually reducing your search space. Now, since each constraint you can have a different specialized inference technique, this means that you can exploit the problem structure, the problem that is represented by the constraint. And exploiting the problem structure relates to operations research. Now, the way how we perform inference does not limit the way how we perform search. You can still apply different search risks that are more suitable to your problem. So this clear separation between model and solution approach refers to AI planning. Okay, so that's why it's in the interface. Now here we are interested in developing inference techniques for disjunctive scattering. So what types of inference do we want? We want two main types. First, we want to deduce precedence relations between activities. And second, we want to reduce the time intervals that activities they need to be processed. And this will, of course, reduce our search space. Now, I'm going to give a very simple example of a type of inference that you can do. For example, suppose that you have three activities. Two of them have release time at 1, deadline at 3, and one release time at 2, deadline at 4. And the processing time, we assume it's 1 for all activities. One thing that you can immediately deduce is that activity 2 can never start first. Why? If you start activity 2 first, then you're going to consume 1 minute of the resource, and then activity 1 and 3, you will violate the deadlines of activity 1 and 3, right? So if you deduce that activity 2 should succeed activities 1 and 3, and therefore the start time of activity 2 must be 3, right? Because you have to process the both activities before starting activity 2. So this is the kind of inference that we are interested in. Now, there have been several sophisticated techniques already. The most popular one, I believe you might already know, it's edge finding and not first, not last week, especially edge finding. And these techniques, they are very popular, and they are actually used in several real industrial applications, but they have several issues. And these issues appears when you have sequence-dependent setup times or processing times, or you have more complex object functions. And this usually happens when you're trying to solve routing problems, or other types of problems where the data is very much sequence-dependent. So what we're going to try to do here is to develop new inference techniques that are based on multi-value decision diagrams. Okay? So what is a multi-value multi-value decision diagram in our context here. So it's a compact way to represent the set of feasible solutions of a problem. For example, suppose that I give you this following problem. I have three variables that have a discrete domain 0 to 3. I want a solution such that satisfies this linear inequality and the variables that are pairwise distinct. Okay? And MDD that represents the set of feasible solutions of this problem is this one. So each layer corresponds to one variable, and the arcs in a layer corresponding to assigning that value to that particular variable. So the paths from the root node R to the terminal T, they represent feasible solutions to your problem. For example, 1, 0, 2, you can see that satisfy all the inequalities and all these more combinatorial constraints. And we say that this is a compact representation of the search tree for your problem. Why? Because regardless if you assign 0 and 1, or 1 and 0 to variables x1 and x2, you don't need to represent these two assignments with different branches. x3 will always assume either value 2 or value 3. Okay, so you don't need to represent the different branches. You can merge these nodes like we are representing here in this picture. Okay, so this is the basic idea of the MDDs. It's a compact representation of the feasible solutions. Now, the fact is that there is a very natural representation of the genetic scattering problems as MDDs. And this stems from the fact that every solution can be represented as a permutation phi, in the sense that phi 1 is the first activity in a resource, phi 2 is the second activity in a resource, and so on. And then once you have a sequence, you can trivially deduce what is the schedule, right? You just need to ensure that the start time of the ith activity is after the previous activity has ended. Okay, this is the only thing you need to ensure. So the idea is that we're going to represent a set of feasible sequences. Namely, the first layer of the MDD can represent the possibilities of the first activity, the second layer, the possibilities of the second activity, and so on. So, for example, suppose I give this, for this disjunctive instance problem, you can represent it with this MDD. So the first activity can only be activity 1, because the deadline is before the release time of these two activities, and then you have all the possible permutations for the other ones. Okay? And if you take a particular path, then this represents the fact that first you are processing activity 1, then you're processing activity 3, and then you're processing activity 2. Okay? And the start times can be easily deduced from that. Okay, now we have two questions. First, how am I going to actually construct these MDDs once I have a disjunctive instance? And second, once I have this MDD, how am I going to perform inference? How am I going to deduce the precedence relations or try to reduce the time intervals that activities can be processed? Well, first start with a construction. And the construction has two main issues. First, finding the most compact MDD, which we call the reduced MDD, is NP hard. It's not hard to see because constructing the MDD is as hard as finding a feasible solution to your problem. And finding a feasible solution is NP hard for genetic scattering when you have release and deadlines. And the second issue is that, except for restricted cases, MDDs they can grow exponentially. So you cannot use them, for real world instances, you cannot construct them exactly. But we are still interested in general cases. We're still interested in solving real world problems. So the idea here is that we're going to, instead of using exact MDDs, we're going to construct relaxed MDDs. In a relaxed MDDs, we're going to control the size of the graph by limiting the number of nodes in a layer, by limiting the width of the graph. I'm going to show you how we're going to do this in the following. And we're going to work with this MDD in the context of with using an operation called filter and refinement, which was proposed by Anderson and Holder in 2 CP papers. Okay? So I'm going to explain what is this filter and refinement. So the idea, how does this work? The idea is that we're going to start with a relaxed MDD. What is a relaxed MDD? It's an MDD that contains all the feasible solutions of your problem, but it may also contain infeasible solutions. The most trivial MDD, relaxed MDD, is a path, where the arc labels they correspond to the domain of the variables. Okay? You can see that all the possible sequences are represented in each of this MDD, but it also contains infeasible sequences. And if you're familiar with CP, this is equivalent to the domain store, okay, to the representation with the permutation of variable domains. Now, what we're going to do? We're going to do two operations, filtering and refinement. Filtering is also equivalent to domain filtering in CP. Namely, we're going to do top-down and bottom-up passes by means of, we're going to scan the MDD from the root to the terminal and from the terminal to the root nodes and try to identify values that don't belong to any feasible solution.
For instance, we might scan MDD and check, oh, 3 doesn't belong to any solution, so I can remove 3. Okay? Now, once we do this, the next operation that we do is what we call refinement. And the idea of refinement is that we are going to add nodes to improve the accuracy of the MDD, to improve the relaxation. And usually this node addition is going to be a risk. For example, what I can do is that I know that this arc it has 2 values. I can split this node into 2 and break this domain, this arc domain, to these 2 values. When I'm doing this, I'm starting to consider these 2 paths separately. And when I start considering these 2 paths separately and apply filter, then I have a stronger inference. So I may be able to remove more values from the domains of these variables. Okay? So I'm gonna perform sequential filter and refinements operations until I have an MDD with the size that I want and as accurate as I need. Okay, so this is the idea. Now, I'm going to show you 2 examples of filterings, or ways how you can perform filtering on MDD. You have other ways. But how you do this is usually you're going to associate a piece of information with each one of these nodes, with each one of the MDD nodes. And we're going to call this piece of information a state of a node. Now, we call it a state because it's closely related to the state of dynamic programming algorithms, but it's also related to the concept of state in AI planning. So, to give you an example, consider that you have this MDD and you want to filter the arc UV. So we're going to associate some state information with this node U, and then for each state information, we're going to apply a particular filter. Okay? So, for example, one of the states that we associate is called the all path state. The all path state contains all the labels that belongs to all paths from the root to the node U. In this case, you only have one label here, 3, that belongs to all paths. Now, let's see. The paths from the root to the node U, they correspond to partial sequences in the machine, in the resource, correspond to sequences, the possibilities of sequences that you performed so far. Now, if you know that in all previous sequences, you have already processed activity 3, you must not process it anymore. So you can already remove activity 3 from the domain of the arc UV. Okay, so then we filter the MDD by doing so. And this was introduced already, this is the same introducing the all different constraint that we can also use for MDDs. But we can also use schedule information. Namely, we can associate the earliest completion time and another U. So again, the paths from R to U, they represent partial sequences. The minimum completion time represents the minimum completion time of all the partial sequences from R to U. So it's the minimum time that all the partial sequences have been processed. They finished processing. And you also can define the latest completion time. And how can you use this information? Well, if you have an agentic instance, and you know that, for example, the minimum completion time of U is 7, then you know, and the deadline of 4 is 6, then you can already eliminate 4 from the domain of UV. Okay, so this is another type of filtering that takes advantage of this top-down information. Okay, good. Now I'm not going to explain refinement, but the idea of refinement is that we're going to break nodes, also use the earliest completion time information. Now I'm going to tell you how we can perform inference using the MDDs. So to perform inference, we have this theorem that it's a very easy observation, but it's key for our purposes. So suppose that you have the exact MDD, not the relaxed one. Okay, you were able to construct the exact. You have a black box that returning you the exact MDD for the genetic instance. The fact is that we can reduce all the implied activity precedences in polynomial time in the size of the MDD n, which is not trivial when you look at it because you start thinking of considering all paths, but you don't need to consider all paths. So the idea is that suppose that you have a node V. Okay, how do you deduce the precedence relation? Suppose that you have a node V. And you collect from the top down all the state information on all paths, all the labels that are in all paths from the root to V. And then you also collect the same information, but from a bottom-up perspective. So all the labels that belongs from all paths from the terminal to the node V. Okay? So, you know, if you have 2 activities, ij, you know that activity I should precede j if for all the nodes V, you never have a relation where they are both inverted, where j begins first than I. This is all of this condition is telling you. So you can collect this information with a very simple dynamic programming argument, and you can use this state to deduce these precedence relations. And what is interesting is that this same theorem also works for relaxed MDDs. The difference is that for relaxed MDDs, we also have infeasible sequences, so you're not going to be able to deduce all the precedence relations. But all the precedence relations that we deduce using this idea from relaxed MDDs are valid. You can prove that. Okay? So once you have these precedence relations, what you can do is you can provide these precedence to the solver, to your searcher, to the way how you're doing, and then you can use this to update the time variables, just like we did in the first example, or some other techniques, some other inference techniques that are more traditional, and you can also take advantage of them to provide a stronger inference. Okay? But you can also do the converse. You can also filter the relaxed MDD using this precedence relations. If you know that an activity I has to precede J, then, and if you have a node with the state that J is preceding I, then you can remove that node, because the node is not going to be feasible in your relaxed MDD. And the interesting thing is that we have examples where even when you consider small widths, the precedence that you deduce using ZMD is not dominated by other techniques, in the sense that the other techniques might not deduce the same precedence. So it's adding to the current framework, it's not being dominated. Now I'm just going to show you some quick experimental results. So we implemented in the state-of-the-art scheduling solver, constraint-based scheduling solver, which is the iLog CP optimizer. It is the state-of-the-art, and what it does is that it uses a portfolio of inference techniques and also uses a linear programming relaxation of the problem. And we're going to test the integration MUD, our filtering, together with the inference that CP optimizer has, by providing these inference relations, these precedence relations, as I described earlier. And we tested with instance of the traveling salesman problem with time windows. So you have to find a Hamiltonian path, but you have to reach the cities within a release time and before a deadline. Okay? And we try to minimize, we tested two objective functions: minimize sum of set of times, which is the same as minimize the total distance traveled. And we know that CP usually doesn't work so well for this type of problems. And minimize makespan, where CP usually works very well. Okay? So what happens? I'm sorry if the points are a little bit small, but I want to show you the backtracks alongside with the time. So this triangle here represents the makespan, and the little black balls represents the set of times, the minimization of set of times. What happens for makespan, and this is in a logarithm scale. So every time that is below the diagonal, it means that they will perform better. Okay? So what happens? For makespan, we didn't have much improvement at all. And this is expected because it's so good that usually the filtering that you provide with this is not so effective. But if you consider set of times, you usually have orders of magnitude improvement, both in the number of backtracks, number of fails, which also reflects in the time that you have to solve this instance. And when we solve it, we find the optimal solution. Okay? We tested with instances from this traditional benchmark with TSP, and we tested this with a width of 16, both with the same type of dynamic search strategy. Now, just for you to have to realize what are these differences, we took some of this data here in the this. Okay. We took some of this data, cities containing between 40 and 60 cities. You can see that the number of backtracks really has this significant reduction. But if you see times, instances where you cannot solve in 1 hour, you cannot solve in 40 seconds. Okay, so we really had, for the case of set of times, it really provided this additional filtering that was lacking before. And my conclusion is that, well, what's interesting to use MDDs for this kind of problems? Because you have a very natural legal presentation, you have this strong relation to the precedence graph that you can explore, and it's a high level of communication between the MDDs and other inference techniques. Okay, and usually this is what filtering does. It never works directly into the domain space. All it has this additional structure that tries to communicate the precedences. In a practical perspective, it's not very hard to implement this in current constraint solver, so I just implement as a global constraint, and we observe orders of magnitude improvements so far for particular object functions that are more complicated. Thank you.
Do we have time for questions? I have one. Which is, you were talking about how there's a relation between this and the precedence relations, and you mentioned a bunch of earlier work on ways of doing filtering based on those precedence relations.
Yes.
Have you looked at whether you could do some of that inference directly on the MDD? I because it looks like the relationship is close enough, but I'm wondering if you can do something like edge finding or the energy filtering, work some of those things directly on that data structure itself.
You can. We have a version of edge finding for entities where we perform them, because entities, when you're doing, you are basically separating some particular paths. And the edge finding is also doing this path separations, but it's exploring somehow the structure of the problem. But we can do a version of edge finding. I'm not sure if this is going to be stronger than the current edge finding because of the properties of how edge finding works. It's usually you're supposed to have this order of the variables, right? It's the sequence, and you're collecting information from the sequence, and as you relax, you're always losing some information. And in the algorithm, in the edge finding, you will not lose this. But what happens is that we cannot take the simply edge finding and consider it in a node because it's a very expensive operation. And we're going to do fast operations with it. Just constant time or a lot of operations are going to be fast.
Other questions?
Yes. Could you explain shortly how to manage to integrate the CPU on a CPU optimizer on an MDD?
How to iterate?
How do you integrate MDD into CPU?
So it's okay. I can explain very fast. So it's CPU optimized, so you can implement this additional global constraints. Right? And usually the SIP engines, what happens is that when you have a modification in one of the variables, it's going to wake up some filtering process. So what we do is that we cheat the filtering process to update the MDD. So every time that some start time variables has been modified, we go to the MDD, we apply one round of top-down and one round of filtering, one round of refinements, one additional round of filtering, so that we try to use. And then we collect these precedents, and then we pose on the start time. So the CPU optimizer has a special structure where you can, when you identify these precedents, you can tell, look, this activity starts before this other one. So we send this information back, and that's how we do this. Okay?
Another question: could this use of MDD be extended to other scheduling problems, other kinds of scheduling problems? Other types of scheduling problems beyond disjunctive scheduling problems.
Definitely. So this is part of a bigger project. So the idea is that we want to complement the domain store with an MDD store.
Yes.
Right? Definitely. So we are also applying these ideas for the sequence constraints, and we are also having very, very nice results because the domain store communicates too little information with these things. And just by considering these additional paths, we can propagate a little bit more. And we are not trying to replace the domain store with MDDs. We are trying to complement it because you can project the MDD to the domain. And definitely we are trying. But then you start having other issues that we are working on. For instance, what is the order of variables that you consider? And in this case, you have a natural order. But yes, it's an ongoing research.
One more question? Thanks very much. Our third talk will be entitled Long-Term Stability and Dynamic Scheduling, presented by Chris Beck.
This is actually PhD work with the first author, Ariel Faircock, who, after great argument, decided she could not come because she's at home working on writing up her PhD thesis. So I'm going to give the presentation, and I'm kind of a planning scheduling guy, dug down at McMaster University as the queuing guy, and so this is how we're trying to come together with this. So the big picture here is I'm interested in looking at dynamic scheduling problems, and so queuing theory is actually a huge area with some very nice theoretical work as well as realistic work on dynamic scheduling problems. They call it dynamic scheduling problems. And so I want to try to understand if it can combine queuing theory and traditional combinatorial scheduling and optimization to better solve dynamic scheduling problems. And so in this paper, we look at a key concept in queuing, which is called stability, which is completely different than what's called stability in the AI scheduling and AI scheduling literature, so I'll define what that is. We show that we can actually prove stability for classical scheduling techniques. And we show that if we empirically apply these classical scheduling techniques to sort of dynamic scheduling problems, we can sometimes outperform the queuing policies. Okay, so that's what I'm going to talk about. Classical scheduling. Okay, so this is a Gantt chart. The idea is we have scarce resources, we have activities we want to execute, and the idea is we have to figure out when these activities are going to execute on these scarce resources to achieve whatever we're trying to achieve. Okay? The strong assumptions of classical scheduling is we know everything. Okay? We know the set of activities, we know the resources, we know the temporal relations if there are any amongst the activities. I'm using activities and jobs interchangeably here. And the challenge is the combinatorics. How can we actually place these activities in time and on the resource to minimize make span, to minimize flow time, to do whatever we want to do in terms of our optimization function. Now there is work on dynamic scheduling, okay, but typically in this framework, dynamic scheduling tends to be periodic static scheduling. So we're going to look at what we have. We have this tool, which is some really great algorithms for static scheduling. We see what has arrived, and we're going to, for a short term, schedule those activities, execute them, see what's arrived again, and do it again. Okay, and that's a bit of a simplification, but it's almost true. Queuing theory. Okay, so this is the study of waiting lines. Jobs arrive dynamically over time, according to some stochastic process, and there's an awful lot of work on saying, well, we assume it's this process, or sometimes they actually have empirical distributions. Processing times, which are called service times, are also stochastic. So we might have different classes of jobs, and each class has its own distribution or own rate with a given distribution. And often, the actual service times are not something you know to begin with. So your job arrives, you don't actually know how long it's going to take exactly until the job ends. Typically, you do have some expected value because it's being drawn from a distribution that you know about, but you don't know how long it's going to be. So, mostly descriptive, so an awful lot of the work in queuing theory says, given a queuing system with these type of characteristics, so you might imagine something like a call center, okay, where you have calls coming in, and maybe it's a multilingual call center, and you have various people who can serve different languages. So, assuming a particular type of distribution for arrivals of different classes and for service times of different classes, can we derive expressions for the values of interest? Can we prove that the expected waiting time of this system is going to be represented by this given function of your parameters? There is some prescriptive work that usually goes under the name of design and control of queues, and we actually did some earlier work looking at a customer service situation where we have frontline customer services, if you want to think about a bank, and in the back room they have to do paperwork. So we have arriving customers that we want to serve, and the workers are going to be shifted dynamically back and forth between the front room, where they're going to deal with the customers, and the back room where they're going to do paperwork. And the idea is we want to shift them back and forth so that they actually get the paperwork done, but also minimize the expected waiting time of the customers. We had a series of papers about that from actually Garrett's master's thesis. So, challenging queuing theory stochastics. Often the combinatorics are very simple, and to some extent, well, in a cynical way, that can be looked at because they are interested in really proving things about the evolution of the system, and the combinatorics really make things really ugly. And so to a great extent, they're thinking about single servers or servers that are configured in a relatively simple way. Stability in queuing theory is basically you want to be able to prove that given the parameters of the system, there is going to be a bounded number of jobs in the system. So you don't want your queues to go to infinity because everything's a big mess. Okay? So this is typically something that queuing theorists do at the beginning of the system when they're analyzing a system before they go further, they want to understand, is this system stable given the arrival rates and the service rates? Often, not always, but often it actually does depend on the decision about how you're going to serve these jobs. So if you pick the jobs out of the queue in the wrong way, it could be unstable, but if you pick them in the right way, it can be stable. Now there are some systems where that's not true. Basically, whatever you do, it's going to be unstable, or whatever you do, it's going to be stable. But there is this interesting area in the middle, interesting from a scheduling perspective, where you can make mistakes. Okay, so long run, queuing is about long-run objectives and stochastic properties. Classical scheduling is about shorter run goals and combinatorics. So if we want to solve dynamic scheduling problems that are stochastic and combinatoric, maybe we can put them together and do something. So that's all in the way of motivation for this line of research we've been doing for a few years. So we're going to talk about stability and show that periodic scheduling methods that use processing time information. So remember, often in queuing, the assumption is you do not have processing time information until the end of the activity. We're going to make the scheduling assumption that when a job arrives, it has been drawn from a distribution, but when it arrives, we actually do know its processing time, which is what we do in scheduling. And secondly, these same methods can sometimes achieve better performance on criteria that we're typically interested in scheduling, like mean flow time. So stability. So we're going to talk about two problems. Two simple problems, because this is really an attempt to try to figure out what is the simplest system where queuing and scheduling disagree with each other. So if we just go for a single machine, basically queuing and scheduling, they're different methods, they end up with the same techniques to how to solve it. So here we've got a dynamic flow chart with two machines. The idea is we're going to have active jobs arriving. At their arrival, we observe the processing times on both their machines. They have to be first served on machine 1, and then served on machine 2. You have queues of infinite size before both machine 1 and machine 2. Another activity will arrive. We're going to assume an exponential distribution with rate lambda in terms of the arrival rates. Again, you see this. Another activity arrives. And also, standard queuing stuff, we're going to assume that the service time on machine 1 is exponential with a rate of mu, and exponential with a rate of mu2 on machine 2. This is what queuing theorists look at and run screaming from the room, because we're going to make the assumption that when the job arrives, as you've been seeing, we know what the processing time is going to be before we start processing. In the queuing literature, this is called tandem queue, but typically they don't allow us to do this. So, scheduling, from a scheduling perspective, we're at time 0. We've observed some activities arriving, some jobs arriving, and somehow we schedule them. Okay? We use some technique to schedule them. We then wait until the machine becomes free. At that point, we observe our system again. Some jobs have arrived. We schedule them again. Give us a second subproblem, and it keeps going. Okay, so this is the scheduling perspective on things. Second problem is a polling system, which is, again, a nice queuing theory model. The idea here is we have different queues of jobs coming in. We have a server here, which is somehow going to physically go to a queue, serve the jobs in the queue somehow, switch to another queue, serve some of those jobs, switch to another queue, serve some of those jobs. We're going to do quite a simple discipline here, so it's cyclic, so we're just going to go around polling it in a round-robin fashion. And the gated discipline means that when we arrive at a queue, all the jobs that are there at arrival time will be processed. If other jobs arrive while we're processing that queue, we're not going to leave, we're not going to do them then, we won't do them until we come around and come back to that. So essentially when we arrive to a queue, we actually have a static scheduling problem, because we know the activities that are there and we know the processing times. Differently from what queuing does, we're actually going to make our server a two-machine flow chart, because we want to add some combinatorics in here so that we can actually do this scheduling and queuing. And make the same assumption. So in this case, okay, from a scheduling perspective, we're at our first queue, we schedule it, and remember, this is a physical change, and so when we physically change, we actually, now it's time 7 that we get to our new queue, observe the jobs and schedule. And so, in fact, where the dynamic flow shop, this job would actually have started back here, right at the end of job 3 on machine 1. Because we're making the assumption that we're moving all these two machines together, we cannot start the next processing until the second machine is done on the previous queue. And that actually surprisingly makes an awful lot of difference in the theoretical stuff, load stability. Okay, so first come, first serve is one way to do this. Okay, it's a kind of a standard first cut queuing thing. We're going to look at the jobs either in the dynamic flow shop or the queuing system and just schedule them in non-decreasing order of their arrival. Okay. We can actually do make span. Okay, so in a scheduling perspective, we're going to look at the jobs and we're going to minimize the make span of that sub-problem. Okay, and another reason we took a two-machine flow shop is a two-machine flow shop is actually polynomial. So there's a technique called Johnson's rule, which will in polynomial time minimize the make span for a two-machine flow shop. And we're going to throw in reverse, which does the opposite of Johnson's rule. But since I didn't tell you what Johnson's rule is, I'm not going to tell you what reverse is. So what can we say about stability? So in the simulation, what we're showing here is the number of jobs in Q0. Okay, this is the polling system data. So we just ran a simulation. Okay, this is simulated time. Jobs are arriving through this time, and this is the number of jobs that are lined up in the queue right at the beginning of the system. So what we see for first come, first serve is actually it never builds up very much. For make span, we have this spike at the beginning, and it tails off and never gets bigger. Okay, reverse. Okay, it actually spikes, and you see these spikes getting larger and larger. So this doesn't prove anything, but this suggests that reverse might be unstable. And so we actually have some intuition as to what's going on. So what we did was we proved, well actually we didn't prove stability of first come, first serve. So first come, first serve, based on what's called the fluid methodology in the queuing literature, we can show that under these conditions, okay, which is basically, this is your arrival rate and this is your service rate. If that's less than 1 on both machines, then first come, first serve policy on a dynamic flow shop, so we're not talking about the polling system, dynamic flow shop, is stable. And if you think about this, if this is not the case, jobs are arriving faster than you can serve them. And so basically you're messed up in any case if those parameters aren't true. Briefly about the fluid methodology. So this is kind of the standard time and standard resource usage. It's a scaling technique that scales both time and resources so that you can model the problem as a continuous fluid in your system. And based on the results in the queuing theory literature, if you can show that on the fluid scale, the total bottleneck workload goes to 0 and stays there, that implies that your original system is stable. And so this is the technique that's used here to do first come, first serve. So the make span is the new thing. And what we do is say, well, let T star n be the time point at which subproblem n is finished. So the final job on machine 2 in subproblem n under the make span approach. And our proposition is that the amount of work completed by that time is maximized by make span in a two-machine flow shop. I'm not going to go into the proof. It's an inductive proof. It's actually pretty straightforward. The corollary there is actually, we've got a simple proof of stability of make span from these two propositions, because basically, if we're completing the most work by the end of the schedule, that means we're completing as much or more work than first come, first serve. As first comes, first serve is stable, so are we. Polling system is different, okay? In particular, proposition 2 and that whole inductive proof doesn't hold. So there's nothing easy there. We can actually show that we can find time points where first come, first serve does more work at the end of the schedule than make span does. So we actually have to go into the fluid methodology to prove this. We did. This is the total number of queues, okay? This is the arrival rate for queue B. And basically what we're looking at is this ends up being the bottleneck utilization. So what you can do to think about it is we're also looking at essentially that lambda over mu1 and lambda over mu2, but we have to identify the bottleneck Q for where that's true. Okay, I'll show you. This is, I see Mark in the back not believing me about induction not working. So here's my counterexample. Here's my make span, okay? And I assume that J3 arrives exactly at the end at time 13, and J4 arrives at 14, okay? So, and independent of how I scheduled it, these are independent processes, okay? So here, under make span, I'm finished at this point. The only job that's arrived at this point is J3, so I schedule it, okay? Here, I've done not as well with this policy, and this first schedule ends at 14, at which point both J3 and J4 have arrived, and therefore I can do better by scheduling them together, and essentially I don't have this gap of time here because they're part of the same subproblem. And so if you look at this time, okay, so this is the end of the second subproblem. First come first, this policy has actually done more work, achieved more work than makespan has at this point. Okay, switching to mean flow time, okay. So we've got some long-term guarantees about stability. Does that really matter for the execution of your system? Part of me says yes, it's kind of nice to have these theoretical claims. Part of me says, well, we're interested in scheduling and getting things through the system, okay. So, so again, what we're doing is we're increasing the Q load. So this is changing the parameters of lambda and mu. So the Q is getting a higher and higher load. As we increase that, our mean flow time goes up, but we don't see much difference between the two systems. Okay? The polling experiments, we do see difference between the two systems. Okay? Same idea. Well, one thing to notice is this axis is completely different. Okay? But also we're getting a significant separation between the two techniques. So what's going on? Well, the summary, dynamic flow chart, it doesn't seem to make a difference. Polling system does, and polling system it does. So, an idea of why this is, we look at this value of C0J. So it's the end time of job J. That could be somewhere out in the schedule. It could have arrived in the kth subproblem. But if we assume that subproblem has actually been scheduled starting at time 0, then that's the completion time of that job. Okay, so to give you a picture, if we look at the end time of job J4, okay, is 9 in our real schedule. If we assume that this problem begins with job 4, right, we end up seeing that time 4 is time 0, and we end up being 5. So in this case, what we can see is the completion time of job 4 minus this idea of the completion time, if we had started at 0, is actually exactly the sum of the processing times on machine 1 from the previous subproblem. Here, in terms of so this is the flow shot, this is the polling system. Here, the case is the shift is actually the make span of the previous subproblem. Okay, so if you think about it, regardless of how I schedule these guys, I'm going to get exactly the same sum of processing times on machine 1. Okay, so if I minimize make span, it doesn't matter because I have to pay that. Here, because it's the make span that's pushing things off, minimizing make span actually does make a difference. Okay, so the polling system actually, the ongoing completion time, which gives you the flow time, it's important to minimize mean make span in your subproblem. All right. That's what I said there. Here's the big picture again. Okay, we've looked at dynamic scheduling and proven that we can minimize make span and show that that policy is stable, and we can show some interesting results in terms of using this make span policy on some problems with some structure. Sometimes it works, sometimes it doesn't. We showed you, we have an idea of why it works in this case. We don't have too much more generally to say about why it works and when it's going to work. That's it.
How strong an assumption do you think, or do you feel the deterministic process is? Do you see any way around it, I guess, or is that just
So I don't think it's a very strong assumption. So I've been doing some work with Google on some of their big data center scheduling, and they actually assume that they know the times that the jobs that are being submitted are going to take. So, I mean, they're assuming right from the beginning that it's a scheduling model. I think more interestingly, what we might want to do to kind of make the queuing theorists a bit happier is we don't actually know the exact processing, the exact duration when it arrives, but we now have a kind of a secondary uncertainty around that duration. Because we've observed this, we have more information than just this general distribution. So maybe we have some sort of normal distribution around a point that we've observed. So I don't think it's a huge problem because I think we do have historic data and people are making these assumptions. Queuing theorists tend to disagree with me.
Well, it seems like there's certain applications where that is pretty true. I mean, if you're talking about computation time,
Yeah.
I mean, that's pretty good.
The question I had just related is, you're talking about that not being a strong assumption. It's also, I mean, at least for some of the queuing work, they really need something similar to stability in some cases. I'm thinking of some work that Carl Kempf did probably 15 years ago. He was looking at a production system. He introduced very small uncertainties in processing time and simulated it. And the queue size was basically, he could go from a very limited queue size and it just blew up. I mean, he said it takes an hour plus or minus 2 minutes, and all of a sudden the queue size has just exploded. So, you know, the queuing theorists may not like it, but at least.
Yeah. And so there's one issue about the realisticness of this, and that's an example. The other issue is, if you don't make the assumption, it's not clear that you can do any better than what the queuing theorists are doing anyway, right? And so if there is some value that's going to be added from the combinatorial scheduling side, this assumption has to be made. And if it's unrealistic, then I need to find some new research to do.
Okay, one more piece of this. Sorry, exploiting my position. Have you looked at more complex scheduling models, or do you have a sense for what that would do with the results you've got here?
So in terms of these ones, if we scale up from 2 machine to n machine flow shops, then all of this, we are confident that all of this goes through. The induction proof doesn't work, but and so we don't have proofs for all these things, but we're confident. We also can have some flexible, where you actually make a choice of which machine a job goes on, which the proofs come through on as well. But going beyond relatively simple flow shop, job shop, we haven't looked at yet.
Other questions? Okay, thanks very much. The last talk for this session, encountering to the job shop scheduling with blocking constraints. So basically, this outline of the talk. First of all, definition of blocking job shop scheduling, our modeling as a constraints expression problem. Next, the contribution from the core contribution of this paper. That's how we solve with this materialistic, we call it iterative pattern research, this problem. And this heuristics is also known as large network search in the research community. So we propose that this heuristic is composed by 2 fundamental steps, relaxation and solving procedure. We propose that these 2 procedures for the blocking option. So some experimental evaluation, conclusion, and investigation. So basically, I want to the blocking job shop scheduling. So to understand the blocking job shop scheduling, we start with the classical job shop scheduling, which is, as well known, is a set of jobs. Each job is a sequence of activities. Each activity requires only one machine, and one machine is required only once a job. The goal is to find for each resource, for a sequence of activity, each resource for each machine. The total order of the activities which require the resource, which satisfy the constraints, the ordering constraints. But the additional, the difference with the classical job shop is the blocking constraint. This means the activity
the machine has no buffering place. So when an activity gets executed, remain to the machine, because there is no way there is no place to buffer it. So for example, we see this, the job, each job follows a route in the shop environment. For example, here we have the job 1, start from the machinery 1, go to the machinery 3, and 1, and next, okay, and the job 2, start from machinery 2, go to the machinery 1, and next go to the machine R3. And about the execution, and the J3, for example, start from machine R2, go to the machine R3, and stops. Observe this fact. When the job 3 starts from machine R2 and finishes, remain on the machine, because the machine R3 is still executing the job 2. So you have to wait the end of the job 2 of the machine in order to move the job from the machine R2 to the machine R3. The same happens for the job 5. Job 5 starts from R2, goes to the machine R1, but when it moves to the activity onto machine R3, we have to wait the end of job 4. So these are the blocking constraints, the effect of the blocking constraints. And the goal, of course, is to find a solution, is an assignment of a start time to the activities which will satisfy the ordering constraints and the blocking constraints, which minimize the total maximum. So this is an optimization problem. And the algorithm for solving this optimization problem is this. This is the meta-heuristic use. Basically, the meta-heuristic gets an input, a solution of the problem, and a maximum number of steps, of attempts. And iteratively apply 2 steps, a relaxation step and a solving step. Basically, the relaxation step is a random relaxation. This means we remove at random some solving decision and actually apply a solving procedure to find a new solution. In case max span is better than the previous one, we just store it. And if you were not able to find a solution within a maximum number of attempts, we just return the best solution found so far. So we just describe now the solving procedure and the chain-based relaxation, how we implement this for the blocking version. And about the solving procedure, this solving procedure is a CSP-based procedure. So, what about the representation of the problem as a constraint satisfaction problem? So basically, we use a classical representation, which is based on the graph G, where the number of the nodes are the activities, and there are 2 kinds of edges. A set of directed edges, which basically represent the presence of constraints among the activity in the jobs, and the set of undirected edges, which represent basically the resource constraints. Okay, and also how we model the blocking constraints. So the present, basically we have to consider, we remember, this is the blocking version of the problem. So basically, one activity, when suppose these 2 activities require the same resource, the green resource, and when the activities arrive to the end time, it remains on the machine until it can move to the next machine. So until the successor of activity on the same job starts on the next machine. So basically, we model this by posting the simple constraints that the end time of this activity must be equal to the start time of the successor activity in the job. And also, we just extend the processing time. So basically, we say an activity can last at least its processing duration, but also we consider the duration, the sum of 2 components, the time, the processing time plus the time which remains blocked on the machine. So, under this hypothesis, the GSOM variable to solve the resource constraints are just for each pair of activities which require the same resource, we can do two things, two possible ordering to solve the resource constraint, to avoid overlapping and considering at the same time the blocking constraints. So, or the activity AI before AJ or the other way around. So, on the basis of this, so our decision variable are this variable O, I, J, R. And on the basis, given the set of temporal constraints underlying the problem, which is classical simple temporal problem, where, so we, on the basis of this, given the simple temporal problem representation, we can calculate distance in time between each pair of time points, each start time and the time of the activities. And so there are other four possibilities. So it's possible, the data are in the paper, but if the distance between the end time of one activity, if these distances are both negative, the problem is not solvable. In this other case, basically, only one possible ordering is possible, and only in this case here, it's possible to take a search decision. It's possible to set a possible ordering between the pair of activities. So basically, the algorithm we are using is a classical CSP solver. So we start a propagation procedure. This means we apply the dominance condition in the previous slides to all the pair of activities which require some resource. We prove the possible. We remove a feasible ordering. In case there is no empty domain, so there is no failure, we just pick one variable on the basis of a variable order heuristic, we pick it, and next we choose a way to order the pair of activities chosen. So basically, the variable ordering constraint we use is based on well-known, the most constraint first principle, and the variable ordering constraint is performed on the basis of the principle of the least constrained value principle. In practice, what we do, for each decision variable, this one, we select the pair of activities which require the same resource, which is closest to the overlapping situation. When we have selected this pair of activities, we post the present constraint, which gives the maximum amount of flexibility, of time flexibility. Okay. What about the relaxation procedure? The relaxation procedure is called chain-based relaxation because, so just observe, when we have a solution, we have imposed a total ordering between the activities, the jobs, which require the same resource. We just select at random with a probability gamma some activities, for example this one, and we remove the activities from the sequence. And this one more, and this activities can be reallocated in different positions on the machine. So this is the first possibility, the first strategy we use very, very easy. The second one is is called the lag-based relaxation. So this is based on the simple observation. When the goal of this procedure is to minimize the next span. So as it is well known, the next span is the length of the critical path of the solution. So if you want to minimize the next span, you have to change the critical path, basically. Then change the length of the critical path. So the idea is to remove at random the activities on the critical path, but also maybe activities which are on paths close to the critical path. Because in general, it is not enough to explore all this space to remove the activities only on the critical path. So basically, we do this very easy reasoning. For each activity, we consider the earliest time solution, and also we consider the flexibility the activity has. That is, we know the total duration, so we also know this flexibility. So this means we can extend the duration of this activity without changing the maximum of the program. So, activity on the critical path has a null flexibility instead of activity which are close to the critical path has more flexibility. So the idea is just to remove activity with this probability, which is gamma in the case the flexibility is 0, or is less than gamma according to this formula. So the smaller is the flexibility, the higher is the probability to be removed. But every activity has the probability to be removed. Okay, these are, now we propose some experimental analysis. So, we use the classical benchmark, which is the Lorentz benchmark, in the blocking version. This is the idea. And also we compare the results with these results available in the literature. There are two journal papers. One is quite recent. And we apply the same CPU, the same settings. So the time, we use the same time used by these authors. And also we have computational power is more or less the same machine used by these authors. I want just to observe, we also have a comparison, they use also the as additional comparison, the iLog, the IBM iLog solver. So we have run together our system. We have also some results by using the CPU optimizer. And we propose a comparison between the two. But just I want to observe this problem, the junction of scheduling with blocking constraints. I think in our community, in ICAPS, this is maybe the first time we proposed this benchmark. So the contribution of this paper is basically we want to show how the application of the large network search procedure in our version, but also the version proposed can be is available within the iLog optimizer, can be very effective to solve this problem. With respect to this result proposed by these authors, which maybe are outside our community and are more close to the WAR community. Basically, these are the results. So basically, we have run the IFS procedure with a random relaxation and a slack-based relaxation with different value of the probability to gamma probability. And these are the number of improved distances according to the different probability of removal. And you see there are some value where there is some maximum value. In this case, for example, we have 13 improvement with respect to the best available literature. And by using the slack-based relaxation, we are able to get better results in average. For example, here we are able to improve 22 instances out of 40. And also, if you count the total number of best solutions obtained, we were able to improve 35 instances out of 40 with respect to the result proposed by these authors here. Okay, in addition, we also, this is a comparison of the CPU optimizer, which works with basically uses this CPU optimizer with the meta heuristics similar to the our flattening, but with different solving procedure. And so what we get, the CPU optimizer is able to improve also over the best results available in the literature. It also, in respect to our results, is only able to improve 11 improvement. With respect to our best improvement, only it improves with respect to our best, so produce 11 better results with respect to the us best results. So in conclusion, So we have proposed that we have solved the blockage Joshua scheduling, which is an interesting model, interesting scheduling model because propose a version of the Joshua scheduling where there is no buffering rule in the machine. Also, and also this problem has application, for example, in the case of the railway scheduling. So in general, it's an hard problem to solve. And we have also proved with a strategy, a meta-heuristic like large network search or iFlat is able to get very interesting results with some recent result proposed in the our literature. And that's the end of the talk. Thanks a lot.
Is there any work on how important the blocking constraint is? So I'm wondering if you take one of the instances and you solve its optimality with the blocking constraint, and you ignore blocking and just solve it as a classical job shop problem. Is the difference in those make spans large or small, or?
It depends from that.
It depends.
But there is difference.
Yeah, I'm sure there's a difference, but I just wonder if it's if that difference is actually, another simple way to approximate would be to ignore it, right? Solve it as a classical job shop and then stick it back in.
Yes.
Right? Given that you already got a schedule, and that would be interesting to know how bad that is.
Yeah, we didn't try this. We can do this and so we can try to make more. Yes, you're right.
So you mentioned the number of improvement, but on average, how much is the improvement in the quality?
No, I don't know this. It is yeah, there is an improvement, maybe 5-10%. That's a number. The number, if you see all the instances.
So I see the table, but it's
yes, it's a large table in the paper. I just was but maybe 5-10% respect to the. I don't see more or less 5% of the max spend, the max spend available in the future.
And on the instant that you do not make improvement and you find the same quality or lower quality.
Very close quality. And you can see there's a list of results for each. Very, very, very close. Yeah. Okay.
Thanks very much. Actually, when I saw it, was it Stockholm or sometimes?
Yeah.